Thank you, Chairman, for the very nice, lengthy introduction. Today, I will discuss pseudogap and quantum hybridization, and then the possible interplay between them in the prototypical heavy-fermion compound, so-called serum cobalt-indium-5. Most of the work that I present has been performed by my student Harim and Hong. So Harim is going to graduate soon, so you need very motivated and bright young postdoctor, then I highly recommend him. He is very wonderful. And then I also acknowledge my fruitful collaboration with Professor Shin Lu from Zhejiang University. Okay, so I think you already heard about enough on pseudogap from the previous plenary talk, so I will not discuss it much, just briefly comment on it. So as you heard that the pseudogap, which encompasses the superconducting state, is an enigmatic quantum phase, which has been considered as crucial to understanding unconventional superconductivity in high-Tccuprates. Observation of the pseudogap in iron-based pnictide, which is another family of unconventional superconductors, has raised very important questions, such as, is pseudogap an ubiquitous phase in unconventional superconductors? Or does it arise owing to the preformed Cooper pairs or other competing interactions? In order to address these outstanding questions, we have studied the prototypical heavy-fermion compound, namely 1-on-5 compound. This compound has been reported to have pseudogap-like phase, and also the energy scale relevant to this system is a milli-electron volt, meaning that is highly controllable via many control parameters. So, for example, in a heavy-fermion compound, serum cobalt-indium-5, Vladimir Sidorov and Los Alamos group reported electrical resistivity as a function of temperature. Here, y-axis is rho minus rho 0 divided by temperature power n. And then what he pointed out, noticed is that at right above the spring transition temperature, there is a deviation from the high temperature scaling, and then he noted possibility as a pseudogap. And then at pressures much higher, then what he notified is that this pseudogap-like phase transitioned to so-called Fermi liquid behavior, and he proposed a phase diagram like this one. So dome of superconductivity centered around 1.5 GPa, and then pseudogap-like suppression, then of lambda Fermi liquid behavior. In STS measurement, also there was evidence. For example, this the differential conductance, this is bias energy, bias voltage. Then at base temperature around 245 millikelvin, then there is sharp suppression due to superconducting energy, and there is additional feature at a wider energy range. And when you increase the temperature to 1.7 Kelvin, and then 5.3 Kelvin, even 7.2 Kelvin, which is higher than TC of 2.3 Kelvin, you can still see, even though the superconducting feature disappeared, there is still a gap-like feature survives. So they attribute it as a pseudogap. And then when applied magnetic field, what they found was that this superconducting gap feature completely suppressed. However, the pseudogap-like feature still survives. And recently, Shrestha et al. In Laura Green's group, they reported planar tunneling spectroscopy. This is the conductance as a function of sample bias voltage. At very low temperature, you can see like a V-shape, like suppression due to superconducting gap in the conductance. And with the increasing temperature, then this gap feature is becomes smaller and smaller. What's remarkable is that this 2.3 Kelvin is where Tc is, but at 2.5 Kelvin and 4 Kelvin, you can still see the gap-like feature. And then ascribed to the pseudogap that has been reported in the STS measurement. So when they plotted it, the gap size as a function of temperature, then what they found was that 0.8 millielectron volt gap size is suppressed with increasing temperature as expected. However, as mentioned, at around Tc, it does not go to 0 as expected, but rather they have a finite value, okay? And then gradually suppressed and extrapolate to 0 at around 5 Kelvin, which they like assign it as a pseudogap temperature. And then they use this gradual crossover as an evidence for preformed Tccuprates as an origin of a pseudogap. However, if you studied heavy-fermion compound, then you know that there are a lot of competing phases around. For example, this is the cadmium, the negative, which is hole doped, and tin doping, which is positive. The electron dropped to the sodium cobalt indium 5. Then you can see that this the Coherence temperature is gradually increased, but the superconductivity shows a dome shape centering around the pure compound, and the antiferromagnetism is in nearby with a very slight amount of cadmium doping, indicating that it's difficult to make a definitive conclusion based on this, or ruling out the other possibility of competing order as an origin of pseudogap. So then Story, he pointed out that in order to distinguish between different scenarios, that you just, it's not enough to just focus on one system configuration, but rather you have to follow the whole phase, like for example, not just the one doping concentration, but rather like use control parameter and see the whole phase diagram. So for example, if the T star is precursor pairing, then you can see that T star ends at the point where Tc go to 0. On the other hand, if you T star is the competing order, then you can see that the end point finish within the superconducting state. If it is well, the system is more complicated, like you have both competing order and the precursor pairing, then it's supposed to be more complicated, but yet it should finish at when the Tc go to 0. So in order to probe the evolution of the pseudogap phase and the superconducting phase, then we used so-called point contact spectroscopy, which can directly probe superconducting gap and pseudogap, and then under pressure. So this technique takes advantage of so-called undirect reflection spectroscopy, where one electron comes in and then it's reflected on the surface of superconducting superconductor, and then making the Cooper pairs in superconductor, meaning that the differential conductance is doubled within this superconducting gap. In an ideal case where there is no contact barrier on the interface. However, if there is an interface on the interface contact barrier, then you can see that now it partially pick up the tunneling. So that's why you have like U-shaped subpollution and then the two peak-like feature in the differential conductance of point-to-contact spectroscopy. So experimentally, we used the two types of pressure cell to do point-to-contact measurement on the pressure. The first is a piston-type cylinder cell, which we used below 2.5 GPa. And then we also used so-called diamond amber cell, which you can measure ideally up to megabar range. Okay, so this is differential conductance as a function of a bias voltage of sodium cobalt indium 5 at ambient pressure in the superconducting state. What you see is that there is a broad background from the final resonance and then enhancement at zero bias due to underleft deflection. So if you, in order to amplify this underleft deflection feature, we divide this conductance by using the funnel. Then what you see is that you have nice two-peak structure that you expect from the superconducting underleft deflection. And then here, the red line is fitting by using BTK, modified BTK model with a gap size about 0.587 millielectron volt. So, I mean, I think we think that the PCS that we observe is intrinsic property and has some meaning. And then we started to do some more quantitative analysis on at other temperatures. So this is the prototypical resistivity behavior as a function of temperature. So basically, you have two rhythms. One, so-called high temperature incoherent rhythm, where the quantum impurity is important and showing the logarithmic divergence. And the low temperature so-called coherent rhythm, which shows a suppression because of the quantum singlet forms a lattice. So this is differential conductance as a function of the bias voltage at high temperature. So the purple line is at 300 Kelvin, which is pretty much flat, well, as expected, because it follows the ohmic behavior. And then with decreasing temperature, then you can see that this, the conductance curve shows a symmetry between a negative bias voltage and positive bias voltage. And we note that the coherence temperature, which shows a peak is around 45 Kelvin, and then the temperature where you start to see the symmetry is higher than 45 Kelvin. So this is temperature dependence. And then in order to quantitatively analyze this differential conductance, we use so-called final resonance model in the Kondo lattice system. And then this conductance curve consists of two parts. The first term is so-called background conductance. The second term is interference term that gives rise to this symmetry. And then the final parameter is complex number with Q1, the so-called final parameter. And the second term, the complex number is directed tunneling into the CF coupled state. And epsilon sub 0 is so-called resonance energy. So in order to fit these data set, we fixed the background conductance and the final parameter in the resonance energy, which, and then even though we fixed them, it explains the data pretty well. So this is the data set at 1.0 GPa, and then, well, the overall feature is pretty similar to ambient pressure. As you can see, a symmetry becomes stronger with decreasing temperature, and then you can see at base temperature, on top of the background, then you have under reflection. So this is the data from 0 to 1, 1.52, 1.8, and 2.34 GPa. So and then those solid lines are the fittings. And these very nice agreement suggested that those final resonance model in the contour lattice system explains the temperature dependence as well as the pressure dependence pretty well. And the other thing is that in all pressure range that we studied, the final resonance of symmetry exists even at temperatures far above transport coherence temperature. And then also at the 1.5 Kelvin that we reached, the zero bias, and then at a little bit higher than the TC, you may see some of the dip appears, which we will discuss later. How many minutes? 10 minutes. Okay, I think I'm going too slow. Okay, so some of the feeding parameters that we use. This is contact resistance as a function of pressure. Initially it drops, and then pretty much is consistent. And then this contour resonance energy and the phonoparameter, they kind of, well, almost flat, gradually increase with increasing pressure as expected, because when you apply pressure, then you increase hybridization. And then the background conductance and inverse of these contact resistance, they are pretty much consistent. Okay, so in order to quantify the final symmetry, we used so-called 10 millivolt criterion. So what we did is compare between minus 10 millivolt value and plus 10 millivolt, and then took the ratio. And then, as you can see, and then the x-axis is the normalized temperature by T, so-called T saturation temperature. T saturation temperature is where you do not see this asymmetry. So you can see that at different pressures, that at high temperature region, then they scaled pretty well together. And with decreasing temperature, then you can see that the deviation temperature from this ambient pressure data, you can see that they increases. And then here the dotted line is the based on so-called twofold model, where it consists of two terms. One is the increase of effective mass, and the other one is so-called autoparameter of the fraction of contour liquid. And you can see that it nicely captures the evolution of the asymmetry as a function of temperature. So in order to make sure that this is not just our arbitrariness of selecting the criterion, what we did was that we used 60 millivolt and 2 millivolt. And all of them, even though they differ quite a lot, then they show a scaling behavior and then deviation at low temperature. So I think this is pretty consistent result. Okay, so and the inset shows the saturation temperature, the red dot. So at ambient pressure 150 Kelvin to 180 Kelvin at high temperature. So note that this temperature is much higher than the so-called coherence temperature. And then this type of, has been already reported in IPS measurement, where they obtained the itinerant for weight. They started not at coherence temperature, but at a much higher temperature. So, which in some sense consistent with our result that the asymmetry comes from the itinerancy of electron. Okay, so this is now go back to the conductance at low temperature. As you can see that this is 1.5 Kelvin. This feature is the undefinite flexion. 3 Kelvin, I think I want to point out this part where you see this is normal state. You see a slight dip at zero bias. Okay, thank you. And this is just amplification of the data at 3 Kelvin. And then after normalizing the funnel, then what you see is that you can see clear a dip develop at 0 bias. And then you can see that the data is actually well above the experimental error bar. So with the increasing temperature, you can see that the dips is suppressed, right? And then at temperatures higher than around 8 Kelvin, it's kind of difficult to observe this feature. And then this is the data near the TC. So these are the dip, right? And the TC is around 2.25 Kelvin. Then slight suppression, 2.25 to 2.24 Kelvin, 236 Kelvin, then you see enhancement near 0 bias, right? So enhancement at 0 bias is due to NDF deflection due to spectral gap, right? That's what you see, the dip switches to NDF deflection. At higher pressure, you can see similar feature, and then you can see that this feature is pretty similar to what you observe in high-Tccuprate. In high-Tccuprate, that this is STS, like measuring tunneling. So you do not see NDF reflection enhancement, but rather you see enhanced suppression and also the coherence peak. Okay, so this is the temperature evolution of pseudogap. Like at ambient pressure, then you can see this is the color contour plot, T as a function of bias voltage. Then you can see that instead of gap is a suppressed increasing temperature, but rather is pretty much insensitive. And then with the increasing pressure, you can see that the size of the gap is enhanced, the pseudogap is enhanced, and then the TG also enhanced. And you can see the similar trend, the size of the gap increases, but it's more or less filling with the increasing temperature, and the pseudogap temperature is increased with the pressure. And this is comparison between the temperature evolution and magnetic field evolution. Magnetic field evolution, what you see, unlike temperature, which does not change its gap size, rather, on the magnetic field, the gap size is suppressed as well as the dip is suppressed. So at 1 point GPa, we can see the similar suppression of the gap size on the magnetic field, and then you can see a similar trend. So, okay, so since I don't think I have much time, I'm just going to summarize it. Here, we have established a so-called quasiparticle scattering spectroscopy, cobalt-105 under extreme conditions, and then which the high temperature symmetry is well explained by the final resonance. And then here, we can see that this dome of superconductivity shows a dome shape centered around 1.5 GPa, and the pseudogap increases, indicating that pseudogap that we observe is not pertinent to preformed Cooper pairs, but rather, as you can see, these are pretty much scaled with other characteristic energy scales relevant to quantum hybridization. So we think that this pseudogap that we observe in 115 is very relevant to the quantum hybridization. With that, we are working on this topic, which means that is it universal to heavy-fermion compound or not? So with that, I'd like to thank you for your attention.
Thank you, Tuson. We have time for 2 questions, I believe. Professor Green.
I'm sorry I didn't make it through your entire talk, but I'm so nervous about mine, I had to run back and forth. So yeah, we have a lot of those, we were the ones that did the photoresonance to begin with, and we did all that stuff. But I also wanted to point out, are you aware of our work that shows that the increasing magnetic field shows that we have a field-induced gap, and that it can be accounted for by Kondo scattering, which is causing the pairing in a composite pairing model.
Yeah, yeah.
Okay.
So in our case, we mainly focused on the high temperature normal state regime. So unfortunately, I think we did not. So this is
Increase in magnetic field. So
right. This is the 3 Kelvin, right? At 3 Kelvin, then so our field is pretty small, I think, compared with US, where you go to superconducting state and apply magnetic field, and then I think you see some feature.
we also do that in what you would call the pseudogap state, which was shown by STM by 2 other groups.
Right,
In our groups, they're just preformed pairs.
Right, so that was actually introduction, then including
Okay.
your work too.
Okay. Yeah, I missed the beginning.
Yeah.
So could you have any, did you look at the pressure induced you looked also just above TC at 3 degrees, right?
Yeah.
Okay, very good, thanks.
Yeah.
Okay, there is another question.
Tuson, when we did that back in, I think, 2009 or so, we got the opening of the pseudogap at about 3.3 Kelvin, in line with the measurements at Los Alamos.
Mm-hmm.
Now, you reported also LoRa's data, and these data were a little bit higher. So
Yeah,
you
5
observed-
Kelvin.
Yeah. Do you have an idea on what this temperature depends on? Is that a surface condition, or any idea what, or does it depend on the measurement you actually do?
I think this, depending on even a tunneling measurement or STS measurement, I think it varies. For example, in the Ali Azdani's paper, even at around 8 Kelvin, they still see pseudogap feature, right? So my guess is, well, I do not have any good argument, but as you pointed out, it may depend on what's the phase you are looking at, and also conditions of your contact. In my case, so those may play a role. That's my guess. So and also, if you look at this part, see, it's kind of very blurry, right? And then, which point you put a T sub z, so at this moment, I don't think I can give you a very good answer.
Okay, the last question belongs to me.
Okay.
Can you go to the last slide?
Okay.
So I like the statement, which is the next one. Yeah. So a new type of pseudogap that is universal to heavy-fermion compounds. So I guess you work also with the other system. Can you tell a few words?
Right, so I think the question is, condor hybridization, you have the denomination gap to heavy-fermion compound, right? That's pretty much, what we know already. So if it's relevant to condor hybridization, right, then why not in other systems? Why just is unique to silicon cobalt indium phosphide, right? So I think that we think that we might see something new. So what we did was that we did some sister compound, and then I think what we see is that at a very high pressure where you already suppress conductivity, this is 5 GPa, 13 GPa, you see some type of pseudogap-like feature that you already see. So at this, it's still under progress. What we say is that maybe we see now cobalt-115, rhodium-115. I think that maybe this is indeed new, novel type of a pseudogap that may be ubiquitous to heavy-fermion compound. That's my guess.
Okay. So finally, let me give you this certificate. This is to certify that Tuson Park has participated in our conference and presented a paper titled as keynote speaker presentation. Let's thank the speaker again.
Okay, thank you.